one of the reasons why this is actually an international conference. He's travelled all the way from Canada to be with us today, so we're very, very grateful to him for that. And it is Professor Rajni Patel. Just by way of introduction, Professor Patel started off his life in the UK, qualifying at the University of Liverpool, so not too far away, and hence why I think he managed to find himself here today without too much difficulty. He then progressed to Cambridge University, where he obtained a PhD in electrical engineering. There then follows a sort of 25-year period of various appointments throughout the world, really, from Sweden, Holland, USA, and eventually in Canada. And it's in Canada now where he's based, and he's the university professor and holds the Canadian Research Chair in Advanced Robotics and Control, and that's at the University of Western Ontario. He's also Director of Engineering at CSTAR, and CSTAR stands for Canadian Surgical Technologies and Advanced Robotics. He's the author of over 300 publications and has a wide array of different interests. Today he's going to share with us his expertise in robotic brachytherapy for prostate cancer. Professor Patel.
Thank you for that kind words. It's always good to be back in the UK. Any opportunity I get to come back, I take it, and I'm very pleased to be here. Probably just warming up a bit.
It's always a bit of a worry at the technologies conference.
I always worry when a Mac follows a Windows system, there's always some problem. Windows following Mac is fine. Okay, so I'm going to talk about some work that I started a while ago. And the reason I've chosen this work is that it's a very good example of the use of robotic technology for an application in medical procedures for treatment of cancer. And this is particularly important because of the fact that prostate cancer is so prevalent in the West, in particular North America and Europe, in Western Europe. One of the things that I'm going to focus on here is to give you an engineering perspective on how this treatment is approached, and more specifically, in my perspective as an engineer on what were the right things to do and perhaps not the right things to do in terms of developing technology. So this is the basic outline of what I'm going to talk about. I'm going to focus very much on brachytherapy, which is a particular approach to brachytherapy, which is the low dose rate or the permanent seed implantation. And I'll explain all of that in a little while. And then we talk about some of the design issues in terms of robotics, and also review some of the systems that have been designed, both as for research and plus some also currently marketed in North America and Europe. So for the engineers amongst you, this is just a quick lesson in anatomy. I'm giving this more to identify the area in which we are working. So if we are looking at problems dealing with this particular organ, the prostate, which is the size of a walnut, And this is an area which, in a sense, is very amenable to robotic assistance. As compared to, say, some of the other areas, like in the chest, for instance, there are people who've been looking at cancer of the lung, where robotics is being applied, but it's not as easy to do as, say, for the prostate. There are complications, though it's not really straightforward. So, as Sir Alfred has mentioned, prostate cancer is one of the leading cancers in the West. In North America, these are the statistics, over 300,000 new cases are reported every year, about 30,000 deaths result from it. And Canada accounts for about 10% of these, primarily the florent of the population. Cancer of the prostate occurs more frequently in men as they age, 30% at the age of 50 and almost 90% at the age of 90. So some people die without even knowing that they had prostate cancer. The main point here is that it's curable when it's diagnosed early enough. And that's one of the things that has happened in the last decade or so, where the cure rate has increased because it is being diagnosed much earlier. This slide is just to show where brachytherapy is particularly applied. In fact, staging of prostate cancer, this is a very simplistic staging. There are more finer aspects to stages 2 and 3. What I'm showing here is that in stage 1 and stage 2, the cancer is still within the prostate. It hasn't spread out outside of the prostate. So brachytherapy is suggested for these two stages. When it goes outside, and it's then it could be applied, but in conjunction with some other form of treatment, such as external beam radiation. These are the basic treatment options for prostate brachytherapy. Watchful waiting. This is, because prostate cancer in many people develops very slowly. So that is one of the standard approaches. Prostatectomy is becoming more and more popular, especially since robotic assistance is now available at a much larger scale than before. In fact, in the United States, the Da Vinci robot is used very, very frequently in doing this. So quite a lot of prostatectomies are being done. This is one of the standard approaches. Chemotherapy is not really very frequently used. Cryo is a new approach. There is not much, there's not more detailed study on the effectiveness of it. This is high frequency focused ultrasound is now coming is being evaluated. Brachytherapy has been used for quite a while, and there are studies of 12 to 15 years to show that it has been quite effective for stage 1 and stage 2 cancers. So there is a lot of interest in brachytherapy. And let's look at that a bit more. So what do we mean by low dose rate brachytherapy? There is another version of brachytherapy, which is the high dose rate, where there is a temporary implantation of the seed and then removal of the seed after. We are going to focus on this because this is the approach that is much more amenable to robotic assistance. And that is the one that's more frequently used in North America and probably in the UK. The idea is to provide local therapy, local radiation therapy, using small radioactive seeds such as these. These are typically iodine 125 or palladium 103. And these are implanted permanently into the prostate. And these are implanted using long, thin, hollow needles, such as shown here. So these seeds are preloaded into these needles, and the needles are inserted into the prostate through the perineum. So, and this is done at the present time in most hospitals in a manual manner, not robotically. In a typical treatment, about 12 to 15 needles are inserted into the prostate, and about, let's say, about 4 or 5 seeds per needle, so close to about 80 seeds are dropped. You can see that if there are 80 seeds being dropped with about 15 needles being inserted into a size of a walnut, there could be quite a lot of trauma to the prostate. And that is one of the difficulties that arises in determining how to drop the seeds and where to drop them. So that's one of the difficulties with trying to do this procedure accurately. The current procedure is this manual seed implantation. What is done is the patient would be evaluated initially. There would be a study done to determine the size of the prostate, its volume, and medical physicists would then determine with an oncologist how much dosage is to be provided to the prostate. And then they would decide where the seeds need to be put in order to achieve that particular dosage. And that would be then, the dosage will be provided then by putting needles through these, to this template. These are the holes in this template which are about 5 millimeters apart, and the needles are inserted one at a time in through those holes according to where the seeds are to be dropped. One of the issues with this is that this actually results in a discrete set of points. So all the needles go parallel because this template is placed right in front of the perineum and the needle is placed, pushed in. And that's another difficulty with, in case of some patients. So once the dosage has been planned and the patient comes back a few weeks later, the seeds are inserted, the patient is then released after a while, and then the patient comes back again, and they do a CT scan to determine where the seeds are. And based on where the seeds have been implanted, the medical physicist will then determine what the dosage of this is, and compare that with the initial dosage and decide whether there is whether the dosage is adequate or not. If not, then they have to add some. They have to go to an initial procedure to try and compensate for the false force. Okay, so that's the current procedure. And this is, the procedure itself has quite a lot of advantages. And obviously, this is being done minimally invasively because all that's happening is that the needles are being inserted into the prostate through the skin. There are fewer surgical complications, say, compared to radical prostatectomy. The hospitalization time is minimized, and there is faster recovery. There are some side effects because of the implantation of seeds into the prostate, but there are much fewer side effects than, say, radical prostatectomy. Now, these are some of the limitations of the manual therapy. I mentioned a few of them. That is, the template allows the clinician to insert seeds in a parallel manner, which creates some difficulties in terms of achieving a proper dosage. There is also this part here, which is limited visual feedback. What's done with the current procedure is that the visual part of it is obtained through ultrasound. Ultrasound that is, in general, 2D. So the clinician does not have a very clear idea about where the needle is or where the seeds have been dropped. There are modifications to these that are being used in some hospitals, depending on the nature of the software that they are available for ultrasound imaging. There is also another problem in that in some patients, the prostate may be swollen because of the fact that the patient may be suffering from what is known as benign prostate hyperplasia, where the prostate grows in size due to the increase in the number of cells in the prostate. What this does is that because the prostate is larger, the needle insertion cannot reach all parts of the prostate because it can be obstructed by the pubic arch. There is an obstruction, and that is the pubic arch creates for achieving all needle insertions into the right spot. Second thing that creates a problem is that as the needles are inserted, the tissue shifts. So when the needle is pushed into the prostate pushes against the bladder, and that creates a difficulty in placing the seeds accurately. The other part is that when you have so many needles being inserted, there is edema, the swelling of the tissue, etc., which is going to cause problems in terms of achieving an accurate dosage. The points where the needle is supposed to be dropped may be shifted, so where the clinician thinks that the seed has to be dropped is not necessarily the right place. So this is an example of essentially what is being done. So here, after a volume study to determine dosimetry planning, the needle is guided and the seed is implanted. And then the patient comes back and the surgeon and the clinician determines where the seeds have been dropped. Now, in terms of dropping the seeds, there is extensive software that's available that will allow the clinician to fairly precisely determine the locations of the seeds. And there are measures available where the clinician will know how much of coverage has been achieved for different parts of the prostate. So for instance, he or she would know that there are certain parts which have received full 100% of the coverage, certain parts have 90%, and so on. So with that background, let me talk a little bit about what we think are the required goals that we need to achieve to convert this to a robotic-assisted procedure. First, with robotics, we are aiming to get much higher accuracy of needle placement. Current practice, the needle accuracy, the placement of seeds is accurate to about between 2 to 5 millimeters. So that if there is, let's say the worst case would be, let's say 5 millimeters, that means that the dosage in that region would not be quite what was expected. So we are hoping to reduce that to between, say, 1 to 2 millimeters by using the robotic system. The other part that's important here is the consistency of seed implantation. In the manual procedure, because of the fact that the prostate can shift, the tissue can deform, etc., there is no control over it. The clinician does not have control over it. With a robotic system, we believe that we can actually control the motion of the prostate and implant seeds accurately. So we can consistently obtain accurate implantation. The other part that's important for this procedure is to be able to avoid critical structures. In the case of implanting seeds manually, we have parallel trajectory, which means that it is almost impossible for the clinician to avoid certain critical structures like the urethra or the bladder or the rectum. So you might end up with a needle actually piercing, say, the bladder if the location of the seed is very close to the boundary of the prostate. The other critical structure, or the other achievement of this robotic system would be to avoid the pubic arch. The pubic arch is a bone that actually comes in front of the prostate, and in order to get behind it, especially if the prostate is large, one would have to have an oblique trajectory, not a parallel one. And so that is something that could be done using a robotic system. So that will be helpful for patients who have got BPH. And of course, we would eliminate the template grids, which will make the robotic system or the technology much easier to use. It's not constrained to a particular device. And hopefully, by doing this as a master-slave system, one could have the clinician sitting at a master console guiding the needles, and that would reduce fatigue on the clinicians. This is basically what's being done with the robotic surgery system. From the perspective of the clinician, it's important that he or she is able to disengage the robotic system whenever he or she needs to. And this is generally true for any robotic system for surgery or therapy. One needs to be able to take over a manual procedure or convert to a manual procedure as soon or at any point in time. And most clinicians feel happy that is there. Now, these features are useful features to have because it's always a good idea to be able to see where all the seeds are being planted and know where the seeds are before you actually start the process. And this could also be useful during the process to update the procedure or to update the seed locations. And from a surgical point of view, these things about cleaning, contamination, sterilization, etc. are important. From a clinician's point of view, reduce complexity in using the system is important. And of course, safety. These are issues that arise every time you talk to a clinician about a new device. So taking all of these into account, for a robotic-assisted brachytherapy system, I've listed here a few of the features that we think are desirable to have. It would be nice to be able to update the dosimetry plan as the seeds are being inserted. And this is currently not possible because there are two stages to this. The patient goes in, has a plan developed, and comes back after a couple of weeks to have the seeds implanted. It would be nice to be able to do this in one shot. Some of the difficulties that one encounters in achieving accurate placement of seeds are because of the fact that animal tissue in general is highly elastic, nonlinear, viscous and all that, and this makes it very difficult for seeds to be implanted accurately. And to control that, it is useful to be able to characterize tissue. In the case of prostate brachytherapy, because we're inserting something like 20 needles, it is possible if you design the system to measure the forces and the positions, and from there to characterize tissue as the needles are being inserted. In other words, the first needle insertion may not be accurate, but as you go further, you get more and more accuracy because you get better and better models. And so this is possible using a robotic system, especially when you design a system that can incorporate force sensibly. And there is a lot of work being done now with people in the area of robotics, where they are developing methods for steering needles. Because needle steering or percutaneous interventions are common not just for brachytherapy, for other areas as well. And it is possible by designing the needles properly and by controlling them using some of the features like rotating a needle or using the bevel tip of the needle to guide the needle, to steer the needle. And this is something that you can do with a robotic system. You can design the control for the robot to be able to steer the needle and to not just insert it in a straight line, but actually make it bend. And that's possible because the brachytherapy needle is flexible. And it would be nice also to have more information for the clinician that provides not just the visual information, but also the sense of touch through haptics. So if you have a mechanism that can measure forces as the needle is being inserted, that force can be translated into a sense of touch using a haptic device. And that would be particularly useful not just for the insertion, but also for training people. Because a person who is a novice would be trained based on trajectories that an expert would have generated. Now, on this slide, I've listed some of the targeting errors, and I've already talked about a few of these errors caused by tissue deformation. That is almost impossible to decide on a priori. Needle insertion, as needles are inserted, you have problems caused by edema and tissue deformation, needle flexing, etc. So these are issues that current technology cannot address, but I think robotic systems can address. This is a video that I obtained from a colleague of mine, which is actually a little bit exaggerated, but it shows you how much flexing can occur in a flexible needle and how you can control the flexing. The needle that's being used here is a bevel tip needle, and the bevel on the needle actually can make the needle bend. So this is a bit of an exaggeration because the needle flexibility is modeled is it's very highly flexible. But by turning the needle, you can actually use the bevel to an advantage. Because the needle tip is beveled, there's a force acting on the beveled edge, which makes the needle bend as you push it through. But by rotating the needle, you can actually make the force compensate as the needle is moving through. And this is something that is being done. Some of the clinicians that I've talked to say that just, intuitively they just rotate the needle as they push it in. And it seems to work. So people have actually worked this out and worked out the force is acting on the needle when the bevel tip is used. But this can only be done if the tip is beveled. If it's a conical tip, then you cannot do this. And then you just have to rely on and hope that the tissue effect is not going to be as significant. So there's an advantage to having a bevel tip. And this is the kind of needle that's commonly used for prostate brachytherapy. Okay, so based on all those considerations, what we have done is to list here a few components that we think every robotic system for prostate brachytherapy should have. So primarily we need imaging. In all medical applications, imaging is a key factor. In the case of the prostate, we are able to use ultrasound imaging. But there are robotic systems that have been developed which use CT or MR. Ultrasound, of course, is widely available, it's the least expensive and so on. The most operating rooms would have an ultrasound system. The robotic system would itself need to have at least 4 or 5 degrees of freedom in order to position and orient and insert the needle and drop the seeds. And those replanning software, hopefully something that can be run in real time would be an advantage. Most of this planning software is optimization based, so that may be an issue. Now, I mentioned that ultrasound that's being used for the manual approach is 2D, but for the robotic system, in order to have image guidance, it would be a good idea to have 3D imaging. And that's something that creates a difficulty. There are current 3D ultrasound imaging systems available which are not quite